So exponential growth and decay. So how we start it is we say the rate of change. That's where this calculus comes from. The rate of change of a quantity p. So that's p prime. Right? Or we're going to write it as dp dt. The rate of change of p with respect to time. If that is directly proportional to p, it translates to this. K, some constant, growth or decay constant is what we'll end up calling it, times p. That's what we start with, if we know that that is true. If we don't, then we wouldn't be able to do these exponential growth and decay problems. But if the rate of change of your quantity is directly proportional to it, and this is obviously directly proportional, it's varied by some constant k. We have this equation, and what we're going to do is we're going to integrate basically and solve that for the growth and decay equation. So I'm going to just do it over here. It's actually all written out. I'm just going to explain what they're doing in each step. So here's what we start with. DEQ is differential equation, meaning it has a derivative in it. So what they're going to do is integrate both sides. Okay, integrate both sides. Now, before they do that, they're going to divide by both sides by p. So basically, they divide both sides by p. So now it cancels over here. There's a p on the bottom there. Okay, so they're just divided first. Then you can see the integral signs in there. So they're going to integrate. So they said separate and integrate. Okay, now this is integration. So it's 1 over p. The antiderivative of 1 over p is ln. Right, natural log p. And then over here we've got integral of k with respect to time is kt. Right, k is just a number. So like 3 would be 3t plus c. Okay, this is it, but we're going to get in a better form, so it looks like that. Hopefully you'll recognize that as traditional exponential growth and decay. We're changing forms. Remember how this is base of e for natural log?
Yeah.
And remember the whole like
Going around town?
yeah, I'm just making something up here, but you do this whole change of forms here, change it to exponential form. So it'd be like e to the 4th power equals x. That's what they do here. E, so the arrow would go around here. E to this power, kt plus c, equals what's left over there, the p. And so that's how they get from that step. They're just changing forms. So the reason is they write in exponential form. Next step is just like e to e squared times e cubed would be e to the 5th. Or I could put x squared times x cubed is x to the 5th. You're adding the exponents. Well, we can also, since these are added, right, I could write this as 2 plus 3. They're going to break it up into 2 exponentials. So as I split into 2 factors. So e to the kt plus c. Well, since those are added, they can write them differently as separate exponentials like that. So they did here. Then, okay, guys, c is a constant, it's a number. Therefore, e to the c power, that's a number to a number, is also just a number. And so this might seem a little strange, but this is a constant number. So they just translated that to say that's just c in itself. It's a number. That became that c right there. Oh, here. Yeah. E to the c is just a number. So they translated that to say, all right, that's just c. Maybe they could have got a different letter there. But it's just c, another number. And finally, c, when time is 0, so if I put in this equation, c e to the, so if time is 0 at the start, we get e to the 0, which is 1, and so the p would be c. And so what they say is, at a time of 0, c would be the initial amount, right? P sub 0 is the initial amount. And so we translate that to this. And that is the general exponential growth or decay formula. So does that look familiar at all from Algebra 2 pre-calc somewhere?
Maybe the unit sounds familiar.
Maybe once we do one, hopefully you'll recognize it as something you've done. What did you say about units?
Like the unit, like we're on, like the exponential.
Oh, okay. Just the topic, yeah. So let me talk about this. So exponential growth looks like this. It's something is growing, and the amount starts here. It's getting a larger amount. Decay would be going down. It would look more like that. They're the same function here, but the only difference is that if it's exponential decay, you're getting less of something, then that k value is negative. Now you see in a minute, you could also have it where you basically treat it as positive, and it'll work out either way, growth or decay, based on the numbers. So you kind of just, even if you don't treat that as a negative for decay, it'll still work out in the end. Okay, let's try one. So this is, again, the main calculus part was right here, doing an integral and getting the formula. You're going to see there's not as much moving forward. Any initial questions I can answer? Let's try a few here. So in a laboratory, the number of E. coli bacteria grows exponentially. So now if it says that, or if it says the rate of change is directly proportional to the amount. Up here. So they say one of those two, then you know it's exponential growth or decay. If they didn't say that, we couldn't assume that we could do this formula. All right, but this one it says it's exponentially. So they give us the growth constant. Not always going to happen. Many times we're going to have to solve for it. And at t equals 0, 1,000 bacteria are present.
Hey, we're gonna get sick.
Well, it's in a laboratory. It's hopefully controlled. They're researching it. But yes. You don't want this to get out. Let's see. So find a formula for the number of bacteria, P of t, at time t. And again, I should go through this. This is the amount. Like not the initial amount, just the amount you have at a certain time. P sub 0 is the initial amount. E is E, number. K is the growth constant or decay constant. It's a common ratio value. And T is time. So we're going to use this formula, and it is exponential growth, right? It says it grows here. So I'm using this first formula. Let me just write it down. By the way, P of T or A of T is usually used. A for amount. So if you see me write P or A, or it could be something else, but generally it's P or A. So P sub 0, E to the K of T. Alright, so let's fill in what we know. At T equals 0, 1,000 bacteria are present. That's the initial amount. So I'm going to put in 1,000 here. E is always just E. They did give us K, the growth constant, 0.41. And we always want the function in terms of t time. Right? So I keep time in there. Okay, that's it for A. Again, you'll see in the next example we do, you're not always going to have K. So we might have to solve for it. But this one, yeah, they gave it to us. So there's the formula we're going to work with, and we'll answer B and C based on that. B, how large is the population after 5 hours? So this is the population function, right? The amount, the number of population. The K was in hours. If it was in minutes or days or something, we'd have to convert 5 hours. But K was in hours. So I'm really just going to be plugging in 5. Basically, I'm doing P of 5. Okay, so let's see. So we got 1,000 E. Yeah, just 0.41 times 5. We'll need a calculator to try some of these out. Actually, a lot in this
Do you know the answer?
Well, maybe, but.
I'm not gonna lie, you have probably the best mental math.
Oh, yeah, but I wouldn't be able to do this one in my head. But thank you. This one I would not be able to do in my head. I'd have to use a calculator. So, you do 1,000 e 0.41 times 5.
Let's see.
Got it.
Yeah. 7,767.90.
Yeah, I thought maybe I had a comma here, but yeah, it looks like I got about 700. Is that what you said?
Yeah.
Rounded, so it's about. Yeah, I guess I rounded to the nearest whole number on this, but I could have done what was it, 0.0?
0.9.
0.9.
It was 7767.90.
Okay, cool. And that is the amount that's bacteria.
She said 77 points, or she said 7767.90. That's what she's saying. But
It's okay.
no, but she's.
Things growing fast.
Yeah, but it's controlled.
Is it?
Well, it's in a laboratory. I'm sure they have it controlled. They grow it so that they can test on it and stuff.
But the government
Or
says everything's
Okay.
Government said
I
contact.
love America. The government.
okay. This is like,
This is one on YouTube. They could listen.
oh yeah.
Got some good things.
Area 51, the whole aliens in Area 51 right now.
Okay. So part C, when will the population reach 10,000? So see, on this, you start with the formula, and then every time you just gotta identify what is provided and what you need. So this one says when. That's asking for time. So we're solving for T. Population 10,000. This is the population at a given time. Not the initial, this is the population. So I'm plugging 10,000 in here for P of T. And then we're solving for T. I mean, so this is, tell me this looks familiar with log equations and solving those. Okay. So I'm going to isolate the E term first. You won't believe how many times I remember in the past, like, students just try and do a log first.
No.
It was, actually, Unit 1, we even reviewed this, solving log equations. You always isolate the exponential term first. So you want to divide by 1,000 first. So we're left with 10. You see that mental math? It's pretty good. 10,000 divided by 1,000. Get it? It's 10. Okay, now that the exponential term is isolated, then we can do an ln to both sides. Throw a log on it. So the left side will be ln 10. The right side, the e's, a natural log of e cancels itself out. And this really, the property of logs really bring that down. So it becomes 0.41t, and then you divide. So, I mean, this is the value. We can put it in our calculator as well if we want more of a decimal number.
Got it. 5.6.
Mm-hmm. What was it, 10? Make sure to close the parenthesis here. Otherwise it probably won't work. Yeah, about 5.62. Let's go with that.
On a test, we're gonna have to find the answer. Or we just leave it like that.
Both are acceptable unless it says round to, round to something. Or write it as a decimal. Okay, so overall I'm glad to hear that at least some of this looks familiar. Maybe a new setting a little bit, growth and decay, but solving exponential log equations and setting them up and going from there. Let's flip it over to another one. Any thoughts on that one? So now, in the next one, I'm not going to give you K. So we'll have to solve for it. So here, it's a similar setup. We got pharmacologists have shown that penicillin leaves a person's bloodstream at a rate proportional to the amount present. So because it says proportional to the amount present, exponential growth or decay. And this is a fact true of most pharmaceutical drugs, even, you know, over-the-counter meds like Tylenol or ibuprofen kind of thing. Because they work for what, you know, 8 to 10 hours or something, they say, or 4 to 6 hours or whatever, in large amount, but then they slowly fade and don't work as much. But there's still trace amounts in your bloodstream at times. So let's see. So write a function to model the amount of penicillin present at any time t after an initial injection of initial amount of 450 milligrams. Okay, so I'm going to set it up with the equation. P of t equals P sub 0 E. Now this one, did you see here, it's leaving a bloodstream. So the amount is getting less. So this is exponential decay. So I am going to throw in a negative here, negative KT. Now, if you forget that, don't worry, because when you actually would have solved for K, if you didn't have the negative there, it would have been a negative K value. So it would have worked out in any case. Okay, so let's do A. Write the function. We have an initial amount of 450. So I'll plug that in at least. And then, sorry, I'm kind of grouping this all, A and B kind of together. That's all we know so far. Yeah, I should write this as like A slash B. That's all I know so far. But then I'm going to get K with the information in part B. So that would be all we know to start. Let's go on to part B. So find the decay constant. That's K. If you have 50 milligrams of penicillin after 7 hours. 7 hours, yeah. After 7 hours after the initial injection. So this is the amount. The amount is P of T. Plug that in. 450 was the initial amount. We already had that.
Already knew.
Yeah. And then 7 hours, that's time. So you see we can solve for K here. It's going to be similar to the last one with solving for T. So it's exponential. We're going to have to throw a log at it in a second, but we're going to isolate the exponential term. So we're dividing both sides by 450. Okay, I like to just write this as a fraction for now. 5 over 45, 1/9. You could leave it as 50 over 450. Right as a decimal if you wanted now. So I got that. Then I got E. I'm going to put the 7 in front, the negative 7K. Okay, we'll throw a natural log at it. So it'll be ln of 1/9 equals negative 7K. And we'll just divide by negative 7. I want to tell you again, so that's our answer is going to be, well, here, watch. Natural log of 1/9. See this one. What is it divided by 7? So this one, watch, is actually negative. So then it turns our final K value positive. Don't round too much here. At least use 3 decimal places. So 0.314. You could write that. But also just leave it in your calculator. We're going to use that in a minute. So what did I say? 0.314. So in our formula then here you can see it's negative, but then K was positive. So it's negative 0.314 when we put it in the equation. So So again, if you had forgotten this negative, it would have worked out in the end because you would have forgotten this and that, and then you would have divided by positive 7, and you would have gotten a negative k value, and then you would have said, okay, it would have been positive here, but then k is negative. It works itself out. So if you don't remember that negative, don't worry, it'll work out. Okay, so in any case, let me get rid of those greens up there, back. Okay, so find the decay, but we found it. That's it. You can write it as if you want to write it as negative just for the question, that's fine. But when we put it in up here, it'll be negative, that number. Okay, and finally, for this one, at what time was 200 milligrams present? So let's see if I can squeeze it in here. I'm going back to my equation here. I'm looking for time. I'm going to put in 200 for the amount. So I'm putting in 200 equals 450 E. Now it's negative and then K, which is 0.314 T. And so if you're solving for K or time, they're both basically the same process, right? I'm going to have to divide by 450, do an ln, and divide. So I'll run through this. It's very similar though to B. So 200 over 450, that's 20 over 45, which is 4/9 as a fraction. But again, you could leave it as this, you could write it as decimal. Throw out a natural log both sides, and then we'll divide. So natural log of 4/9, negative 0.314 T, and then divide here. For time's sake, let's just give it to you about 2.583 is what I got. And this was, time was measured in hours, the amount was milligrams. Let's see. So how about now that we solved for a k value there, anything I can answer on the second one? Not too bad. Again, as we keep going though, we give you different information and so I'm trying to decide which ones I'm going to tackle here.
What's the process?
Natural log of E is 1, right? And that disappears.
Yeah. Yeah, so really you use the property of logs that brings this down. Then, so it's in front, but then natural log of E is 1. Yeah. Because really it's, natural log of E, it has a base of E. And those cancel E. I think I'm going to go to the next page. I like that one at the bottom, but I mainly want to just summarize it in this formula on the next page. So I think I'm just going to go to the next page. And what we would have done in the last example is, if you're exactly doubling something, there's a formula that happens. And it also holds true for half-life. So how about half-life? You guys done that in science? Or
Oh yeah, basic biology.
radioactive elements? Something with half-life, we talked about it. So this formula that I'm going to show you how we get it, it works for if you're doubling something like business, you want to double the amount of money you have. How long will it take under a certain interest rate? It'll also work for half-life. Okay. So we start with our basic formula. I'm working with like it's doubling, but it's going to work the same if it's half-life. We're going to have double the amount. So we're going to start with some initial amount, and over here it's going to be double. I'm going to choose just a number. So let's go with, I start with 100, maybe $100 or something. I'll go again. So what's, if I want to double, that's what I'm looking at. What's P of T? 2P of P sub 0, which is 2 times 100, so 200. It's not going to matter what you start with because we're going to divide by 100. It's going to be 2 on the left side no matter what here. I'm going to leave it in terms of KT here. So the growth constant is positive. We don't know what K or T is right now. Okay, well the initial amount is 100. We want to get to 200. So I'm going to solve this equation and get a nice little formula. So we can divide by 100, kind of as we've normally been doing. Right, so we get 2 over here. And then I'm going to do, kind of as we've been doing, natural log both sides. So here's what we get. ln of 2 equals kt. And then from here, you can divide, if you want time, you can divide by k. If you want k, you divide by time. So down here, they generally want doubling time, so t. So I'm going to divide by k. And let's see. So t, the time, is going to be ln 2 over k. So again, this only works if they say something about doubling. You're getting exactly double the amount. It also works for half-life. I'll show you in a second. That's the value. Now, if you wanted time, it's ln 2 over k. If you wanted k, so you could just cross-multiply, like reverse these variables, and it would be ln 2 over t equals k. So maybe if they say, what is k, and you know the time, the doubling time. So this here is the doubling time. How much time it takes to double the amount you have. So that's doubling time. I showed you this one. K is greater than 0. Half-life, it's exactly the same. Now you might say, wait, shouldn't it be different? Shouldn't it be negative? Well, let me show you. Let me show you it's not necessarily going to happen. Let's do the same thing. I'll start with, I have a substance, or it could be business and money. I start with $100, but how long until I get half of it? Okay, so it could be an amount, 100, or I have half of it left over. Now it's decaying, so I got to put a negative in there, and we're getting less than an amount. So let's solve this, and you might say it's going to be different or negative. Well, it's actually going to be the exact same. So let's see, it's divide by 100. So 50 over 100, I'm just write it as a half. Equals e the negative kt. We'll do an ln. Okay, we'll do an ln. So I got ln of a half, or you can write 0.5 if you want. Over here I got negative kt. I got negative kt. Now, as before, we could solve for k or t. But if they want half-life, that's time. The amount of time it takes for half of a substance to remain. So let's solve for t again. Divide by negative k. Okay, there we go. Now you might say, wait, that is not at all equal to this. Well, let me show you that back here, ln of 2 0.69, ln of half, or 0.5, is negative 0.69. So when I go over here, so these are actually the same, but they differ by a negative number. And that's where this negative and the negative from here actually cancel out. So it would be the same. So really what I could do, I could replace this right here with ln2, but it's got to be the negative version. And then I could cancel those negatives out. And so we're left with ln2 over k. Another way to look at it, guys, ln 1/2, you could write as 2 to the negative 1 power. Because the 2 on bottom is to the first power. I could make it 2 to the negative 1 power. Properties of logs say you can bring the negative in front. And then there was this negative on bottom that cancels out. And so we get that. So it is the exact same. You think it should be different, but it's exactly the same. Okay, so I showed you how we developed it. Let me give you an example. Again, this only works if they say double, something's doubling, or it is half-life. Giving half the amount. If they say tripling, quadrupling, or a third or something, it's not actually that different. You would plug in instead of 200 here, if they say triple, 300, and you can work it out. Any thoughts on that before I show you one? So the isotope radon-222 decays exponentially with a half-life of 3.825 days. How long will it take for 80% of the isotope to decay?
That's not
In oh well, that's true. That's true. Not what it's asking for, but we go with the fact that we have the half-life. So I'll show you both ways. The easiest way to do this is just to get my K value up here from this. Okay, but I could also set it up. I'll show you that as well. All right, so one way to do it here, I need K because this is the half-life. Okay. So half-life, for half-life up here, it was K equals ln2 over t. Basically, they give us 3.825. I wrote that backwards. Oh, here, I'm sorry. I wrote it on yours. I said right here, writing these, if you solve for the other variable, it would be this. Just interchanging K and T. See that on your paper?
Yeah.
So we can interchange them, and this is, if I want K, it's this formula. If I want T, I would just use ln2 over K. So I can get my K value by doing ln2 over the time. This is the half-life time, which is 3.825. Okay, and that's K. I'll probably need a decimal here, so. Divided by 3.8. So I'll use that in a second, about 0.181. So I want to show you, if you had forgotten this formula, no worries. You would just set it up like this. Choose some amount. 100 is what I like to start with. 50 would be left if you're doing half-life. E to its decaying, negative K. And then you put in the half-life, 3.825. So I'm just telling you, if you forgot that formula, you do that and you solve like we've been doing for K, and you get this. First, I'm not going to do this one again, but you would solve and get that. That works out. Okay, so for ours, let's solve. They want how long? That's time. So again, this was just optional. Another way to get K, if you wanted. How long will it take for 80% to decay? So we need an amount that we have. So if 80% is decayed, then 20% is left. Right? 20% remains.
Yeah.
Okay. So let's set up our equation. P of t equals the initial amount. Now, they didn't give us any initial amount, right? That's fine. I make one up. I basically always choose 100. Let me choose one. That's fine. I don't know. I just like 100. Now, 20%. This is our initial amount. 20% is left over. 80% is decayed. So we're we're at 20. I think that's why I choose 100, because then it's easy to compute the 20% left. E to the negative, because it's decay, I put in k, 0.181. And then here's time, and that's what we're solving for. Okay. So it's just another solve. It's going to look familiar. So I'm solving for time. Divide by 100 first. 20, well, 2 divided by 10, I got 0.2. So 0.2 equals, I got e to the negative 0.181 t. Do an ln on both sides. So let's say I got ln 0.2. And then this is all that's left, and I'll be dividing by negative 0.181. Okay, I just put that in, and that'll be the time. By the way, notice that I'm just going to do ln2 divided by and use the previous answer. So I think I said negative. So negative, and then just use the previous answer. What did I do here? Put it in right. No, it's 0.2. Oh, I did? Oh. Thank you. So I was like, the work seems great. ln of 0.2, okay, divided by this answer up here. Oh gosh, why did I hit divide 3 times? Okay, this is 0.2. That's probably just wrong. Okay. Well, I meant to have it be negative 0.181. Anyways, it should be positive then, 8.9, 8.88. Let's write that's about 8.8, and this was, t was in days.